Hello, and thank you for joining us at Coalesce. My name is Elise Papineau, and I am a Senior Analytics Engineer at DBT Labs. I'll be the host for this session. The title of this session is Operationalizing Column Name Contracts with DBT Plier, and will be presented by Emily Ruder, who is a Senior Analytics Manager at Capital One. Before we get started, I just want to point out that all chat conversation for this presentation is taking place in the Coalesce-column-name-contracts channel in the DBT Slack. If you're not a part of that chat, you have time to join right now. Please visit community.getdbt.com and then search for the channel Coalesce-column-name-contracts when you enter the space. I feel like I'm reading documentation aloud here. We encourage you to ask other attendees questions. Please make comments, react in the channel. We're all here together doing this interactively. After the session, the speaker will be available in the Slack channel to answer your questions. However, we encourage you to ask those questions as they come up at any time. Okay, let's get started. Over to you, Emily.
Hi, everyone. Thank you so much for coming today, and I'm thrilled to be here at CoalesceConf to talk about how we can use column names to fuel more robust data pipelines. So I think really one main reflection over this conference is we have so many great tools now to tackle the technical challenges of the modern data stack, from everything from extracting and loading data all the way through that last mile testing and documentation. But there's still some glue that's missing to tie all these pieces together, and I don't just mean an orchestration engine. I would argue that some of the people challenges are not fully solved. There's a sense of communication that needs to exist and persist throughout our whole data pipeline, or a lot of the work goes to waste. And that communication can take many different forms, between different data engineers and analytics engineers handling different steps of this process, or between data users or data producers. A different way to think about this is each step relies on a shared set of expectations of what the input and what the output is going to be, or else no matter how good our pipelines are, how technically correct they are in terms of our understandings of the specs, they feel wrong and they'll seem wrong. I suspect everyone here today has probably already been on one side of this dilemma, where either we as users think data's broken, our pipeline's not flowing through, simply because some upstream engineer actually has that data loading at a different cadence than we expected, or a metric doesn't behave as we expect because two different business users had a different concept of what a certain business concept or variable was supposed to act. So without clear expectations and a clear understanding between users, data quality is in really serious jeopardy. And put a little more simply, we need some sort of contract between all of our data producers and all of our data users to build a really good data pipeline. And if I think about what other things persist throughout this whole life cycle that we can maybe attach those contracts to, I think about column names. So I came onto this idea of what if column names could be that contract, that thing that persists really rich metadata throughout the whole process and aligns all of the stakeholders in building our data pipeline. And of course, all of us that are here at Coalesce really love the modern data stack because it's pulled all of these best practices from technology and software engineering, DevOps, into the process of making data. So naturally, when I started to think about how do we form these contracts, I turned to more inspiration from the software engineering world. And I thought of three main ways that contracts can get made in software products. The three that I came up with were through interfaces, through configs, and through code itself. And to put a little finer point on that, interfaces really help developers communicate with end users. Configs can help developers communicate with other developers. And finally, code helps developers communicate with machines that are actually the ones that do all of the heavy lifting. So this whole got me thinking, how could column names effectively pursue all of these three purposes? How can column names act as interfaces, act as configs, and act as code? And that is what I want to explore today, with the help, of course, of both DBT and a package that I've recently developed called DBT Platter. So first, let's start at the beginning. How can column names act like interfaces? To answer this question, first we have to think a little bit about what interfaces are. And they're that layer on top of the data, on top of any sort of tool that is what users actually see and interact with. And I think it's pretty clear that's what column names do. They're the things that we type in our code and benefit from the rich underlying functionality of the data that lingers behind those names. And you might question on this slide why I say that data has functionality. After all, isn't it just some static artifact? But I actually think data is a very living and breathing thing that is very important to think of as the functionality it has that can be communicated through an interface. So for a brief example of this, we can even think of something as basic as a login flow. If I'm modeling data for a user login to some sort of an app, I can think about the complex process that symbolizes login, from loading a page, typing username and password, entering CAPTCHA to prove you aren't a robot, clicking some buttons, hoping to get verified, doing multi-factor authentication, and finally, if all of that works, the user logs in. But if I want to model one single login event, one single login table, I'm forced as an analytics engineer to make a ton of decisions about how all of that functionality in the data engineering process should show up in my data. There's a very clear who, what, when, where, why of what are we representing, where does it come from, when does it manifest, and all of these things are things that we have to keep in mind when producing data, and our users have to keep in mind while consuming that data. And it can have massive impacts on the results. Simply by thinking about which of these 16 events we actually decide to define as that login event can have massive implications on which records get loaded into an end table, what's considered a success and failure, and could even dramatically impact what an analyst might calculate as a metric as simple as the login rate. So all of this sort of functionality are the things that we ideally would want our data interface to capture. And I think we can learn more useful lessons by thinking about how interfaces usually capture some sort of this function. For example, they might use universal symbols to communicate intent, for a trash can to delete things, or a floppy disk to save items, which is really intuitive, at least if you're old enough like me to remember what a floppy disk is. Next, interfaces can use grouping and put like things together. If I know what something's nearby, I have a good chance to think that maybe it's similar purpose. And finally, we have aesthetics. Bright colored buttons and colors can communicate things like places where caution is necessary. And these sorts of symbols can map really closely to the kind of functionality that we might want to hint our users about in our data. For example, we might want universal symbols to denote things like, yes, I'm a binary variable. Grouping could help us find all of our binary variables together in one place very easily. And aesthetics and warnings could help encode and warn us when those binary variables might or might not have nulls. So hopefully some of this has intrigued you into why our column names might want to act like interfaces. But next, I want to get a little more tactical about how we might do that. And I propose a two-step approach using a controlled vocabulary. First, we can define a simple set of stubs that encodes a lot of those semantics, those who, what, when, where, why questions that we asked before, and carries along some of these performance contracts. Second, when we go to name our columns, we can simply compose these very simple stubs that have very clear specific meanings into a permutation of rich and complex concepts that really clearly characterize our data. So I'll walk through a brief example of this, and I don't pretend that you'd have to use the exact same controlled vocabulary I do. I just want to show the underlying principles at work. So as one example, we could have our first level of stubs be sort of a layer that represents the different types and purposes of variables, like indicator variables, count variables as n, date variables as dt. These are probably like prefixes that you've used or seen before. But we could go a step further by defining very clear and specific semantics for each one of these stubs. For example, an int variable is a binary 0-1 variable, And critically, we could specify that the rest of the name always defines the condition that's tagged as 1. Eliminate that ambiguity that can result in people sometimes incidentally flipping the sign. But beyond just communicating semantics, these stubs can also communicate performance contracts. So you might notice that end and bin have similar semantics, but we could further define something like end to also require that the variable is always not null, whereas bin might be a little more permissive. Similarly, we could promise our users that date variables are always in 8601 ISO format. And you can imagine this extending to subsequent layers of a controlled vocabulary. Next, perhaps having an entity layer that defines concepts like user and login. Once again, we could eliminate that confusion of what on earth is a login by attaching these stubs to very clear and specific semantics. And in addition to contracts, these stubs can also carry along with them consequences. For example, if we decide to define unique users by their IP address, we know that in some cases that might or might not be unique. So every time someone encounters the stub user in data, they should have that in the back of their mind. And this can be a very, very powerful exercise, even just going through the process of defining these stubs with our business stakeholders. Because by having these rich discussions about what every single word in our data set should mean, we also get a very clear sense of what it isn't. We eliminate all of that ambiguity and can drive towards more consistency throughout an entire data mart. So putting this all together, you can imagine us defining more subsequent layers of possible stubs, and when we go to define our column names, permeating these together into those really rich and expressive concepts that are immediately intuitive. And now let's drew back to some of the ways that we thought about building an interface before and see how stubs can serve all of these purposes. We'll see how universal symbols can fuel programmatic wrangling, how they enable grouping, which aids in data discoverability, and how they act like aesthetics that can communicate warnings and type hints. First, using these universal symbols can make it easier to wrangle data. For example, if I'm a data analyst using data that was set up this way, and I want to take the mean of all indicator variables in my dataset, I can very easily manipulate all of the column names, extract all of the variables that start with end, and apply a transformation to those. Secondly, by grouping things with similar names, UIs can make it easier to find the fields we need. It makes them more immediately searchable, or if we're using a nice IDE that has autocomplete, simply by typing the beginning of that name, we can pull up all variables of a similar type and easily browse through them to find the one that we need. And finally, Data UI can increase the caution in a dataset by helping users use fields correctly. If I want to calculate the rate of successful logins in my dataset, and I just have a login field that maybe I don't realize can have nulls, maybe I don't realize that it's only considered a yes or no once it's past CAPTCHA, if I actually just take the mean of the login column, I might think I was calculating the proportion of successful logins, but I'm actually calculating the proportion of successful logins conditional on completing some actual step. By not understanding that data had nulls, I could fundamentally be calculating a different business concept altogether. But if my variables are more meticulously named with ind or ben, I either know that I can take that average confidently with no sorts of transformations required, or in the case of a bin variable, I know that I maybe have to apply additional treatments to that variable to get it in the state that I need. But with either of those outcomes, it's much more apparent what I, wearing my analyst hat, need to do because I understand inherently what data analytics engineers already did. So in these ways, column names can be a very powerful interface for developers to communicate how data is intended to work to data consumers. But the benefits don't stop there, because column names can actually also act as configs and make life easier for us as the data developers ourselves. And we can see this by reflecting on first, what is a config file? And of course, all of us that use DBT are very familiar with config files and know that they're a very good way to efficiently collect out inputs that are used throughout our project. And hopefully you can already start to see the connection between config files and defining stubs in a controlled vocabulary. Thinking back to some of the stubs we defined before and their related contracts, that immediately helps guide us as data analytics engineers how we need to treat that data and what sort of steps we should take when producing them. For example, if I wanted to code up a bunch of tests using something like Great Expectations to test that all of my contracts in this data set were met, I don't have to spend a lot of time reinventing the wheel and thinking about what checks do I need to do. And the reason for that is because those are implicitly tied in the contracts themselves. For all n variables, I know I should be checking those are integers, etc. It's pre-specified for me. And these config files are really nice too, because they embed this concept of enter input one place and use it everywhere, because these stubs can actually have a lot of power to drive standardization throughout an entire data pipeline. For example, before we even start a project, they can help us create a shared understanding between data producers and data consumers. They can set correct expectations for when that data will be available and loading. They can reduce kind of the mental overhead when we're manipulating this data of what should we name it, because that's pre-specified. And as we just saw, they can aid in figuring out what tests to run and are pretty self-documenting, pretty explicitly clear from the names themselves what that variable is doing. But beyond being input once, use everywhere, in my mind, an even bigger benefit as a developer is their ability to help us drive consistency by being change once, update everywhere. So suppose we're going along, once again, building our logins data pipeline, and when we reach the testing stage, we realize, oh, the non-null test is failing. And we think through the logic, and we realize for some fundamental reason, that variable absolutely has to have nulls sometimes. Now, in kind of an ordinary workflow, you might put some Band-Aid fix on at this stage and only continue to move forward. But in fact, by using these names, we're guided through the whole process of thinking of all of the changes we need to make and all of the implications that this change has on our data pipeline. So for example, realizing that data must have nulls, we know that data probably needs to have a different name, and that kind of pulls us back to the beginning of the process, thinking about how we're extracting it differently, where the nulls are coming from, and renaming that and massaging the data accordingly. This also immediately helps trigger in our minds if we need to be applying different transformations to the data than we were previously. And similarly, different tests. We obviously don't want to run a non-null test on a variable that we're explicitly allowing to have nulls. And finally, because of the self-documenting nature, we know that once we've changed the name, that variable has different meaning. It has different intrinsic properties that should be communicated through any data dictionaries and metadata. So when column names act as config files, they have this very powerful ability to help analytics engineers immediately understand what are the steps in the process I need to enact to build high quality data. But even better is if column names could not just be that dictator that tells us what to do. It'd be nice if they were more of a true partner in the process and actually help do the heavy lifting themselves. And this is where we reach the point of thinking about column names as code. Because so far, when we've just talked about intent, there are a lot of benefits, but there are also a lot of inherent risks. For example, bad contracts can really be worse than no contracts at all. If we've made users these promises but don't deliver, we can drive inconsistency with names with a lot of typos that make it harder for users to actually write simple queries. We can cause infidelity, where we've promised users that we're upholding certain data quality checks, but we actually aren't. Or through too much automation, we can actually evade detection of errors instead of actually solving for them. But by regarding column names as code, code can help us turn this theory methodically into practice. And this is particularly aided with the help of DBT. For example, we can use Jinja templates to drive that consistency and avoid typos. We can increase the fidelity of our data through both using custom macros and DBT plier. And finally, we can improve accuracy with in-pipeline testing. So for the rest of this talk, I want to get a little more tactical about how to put these ideas into practice. But first, to do that, I want to say a few words about my package, which is intended to help in the process. dbtplier is intended to help maximize the benefit of column name contracts by providing some nice helper functions that allow you to quickly select out columns based on certain properties of stubs that appear in the name, such as column names that start with, end with, or contain certain key phrases, and then apply transformations more iteratively over a set of column names, either in a select clause or even in a where statement clause. And all of the syntax here and a lot of the underlying philosophy of this approach is heavily inspired by the excellent R package dplyr, which is really a case study in great design, which has very much been an inspiration for me in this work. So to give a little bit clearer of a view of how this actually works, I'll show just one quick example. So here we can use dbtplier to both get all of the column names out of a data set that we intend to work with and subset a list of columns that are only the column names in that table that start with end. And then we could write a query using the across function to apply an average transformation to all of my indicator variables. And when that query is rendered, get one nice statement or one nice row in our code, taking the average of every single indicator variable we found in the previous step. And similarly, if we wanted to, we could apply similar sorts of transformations, similar sorts of iterations in the where clause as well. So thinking about then both dbt and dbtplier, we'll see how we can put some of these ideas into practice. The first situation we might want to avoid is breaking our contracts in ways that really frustrate users. Like I mentioned, we could have those dreaded typos where we either put stubs in the wrong order, miss a letter out of one stub, and make it really hard to remember which of those variable names is a little bit different when we go to write a query. So to mediate this, ideally, we'd probably have some, perfect SQL script where every single one of those transformations is written completely and correctly and spelled correctly. But the more of these transformations we add into our data, the higher the risk that we do something wrong at some step along the way. So to mediate this, what we can do is we can instead define any conditions that we want to iterate over and use Jinja templates like a for loop to create that consistency in our logic only once, so we can't mess up either on the logic or on the naming conventions themselves, and dynamically create those variables. Of course, even worse than frustrating users is lying to them. And that's what we do if we break the contracts we've promised them. If I have a variable like date login, and I want to use that to figure out how many users logged in on a certain date, if I filter that data as if date is a date variable, but it's actually a timestamp, the kind of horrifying thing that could happen is I could end up with 0 results, not at all what I was looking for. And that would essentially be helping our data lie to our users. So clearly what we'd want to do is ensure that always, every time we're using one of these variables, we're casting them to the correct data type that we promised users. And we could do this manually, but if we later add a new column or field to our data set, that means we might forget to add it to this step of the pipeline. There's a risk that we don't keep things totally consistent. But once again, this is where both custom macros and dbtplier can enforce this consistency. We can write logic that extracts all of the column names, again with a field like date in the name, and applies a transformation, casting it to the date in a way that's flexible enough to adjust when new fields are added to the pipeline. Of course, you can imagine cases where this might actually break down. Casting might be great for a date field that could handle timestamps, but think for a minute what happens if we just blindly cast fields to integers. If our data looks like the underlying data in column NA, which is integer, but just doesn't have those zeros chopped off, this transformation works great. However, if our data is like data in NB, where it feels like something went wrong earlier in our pipeline, by casting it, we're not actually solving that problem, we're just hiding it. And that's not good either. So that really motivates the need for testing any unenforceable contracts. And this is another great use for DBT's internal testing functionality. Once again, ideally for a case like this, we would test for every single n variable before we do that cast integer, that the absolute difference between the casted and the uncasted versions was pretty trivial. But once again, if we add a new column to the dataset, there are ways that this test could become brittle or obsolete or not sufficiently robust. But if instead we wrote this test using DBT and dbtplyr, we can once again make it more dynamic, pull out all of the variables that start with n in the name, and automate this test so it will always apply to all of our n variables in a flexible way. Finally, the other exciting thing we can do is test metadata properties of our data and not just data itself. For example, another way this could become really annoying for users is if we're consistent but incorrect. Say I define in my controlled vocabulary that all of my fields should start with n, but in reality, all of them start with num. That's going to make it really annoying to query. But the final type of tests that we can write help us test names themselves and not just the values. So by querying our data's information schema and breaking apart the components, we can test that only allowed stubs are in our data and easily identify any invalid name components with normal DBT testing. Similarly, we can also test the correct mix between stubs and data types. Once again, query the information schema, break apart the components, and filter to make sure we're only allowing correct combinations of stubs and data types in the dataset. So by using the power of DBT, we can transform this theory into practice and in a really rich way to automate a lot of the busy work of building robust pipelines that are very consistent, very faithful to our intent, and highly accurate. And this completes our journey of how column names can act very richly as interfaces, configs, and code as we build a data pipeline. So in summary, to build a good data pipeline requires excellent communication between all stakeholders and between the many different steps and tools we have in the process. And because we need those communication to exist throughout the whole process, we need to embed them in something else that lasts throughout every step. And column names can be a very effective way to communicate throughout this data lifecycle. For this reason, column names can be very effective contracts with a little bit of discipline and a little bit of foresight to add a ton of value in building very communicative, very intuitive, and very robust pipelines. Thank you.
Wow, thank you so much, Emily. That was inspirational, and I definitely leave that wanting to implement dbtplyr on a few of my current projects. So that was really exciting for me personally. We do have a couple minutes for questions here, and we have a couple minutes from a couple questions from Slack. I'm going to read aloud. Please forgive me if I mispronounce any names. So the first question is from Josh Temple. What's the role of column metadata in this type of system? For example, binary is a data type. What's the reason for also including it in the column name?
I think that's a really interesting question. And I think it actually relates to a related concept called Hungarian notation that like way back when in the earlier days of, I think, C and C+ programming was a thing. I think the distinction I make is I agree that it would be silly to include in column names things that are like purely just type information in a way. Because like you say, you can get that in other places. You can get it from metadata, from information schemas. But I think in my mind, probably, I think part of that distinction is when those kind of like type information crosses over, so it's not just about the type of, yes, this is an integer, but when it starts to hint a little more at the actual functionality and semantic meaning of that data set. So I don't necessarily care something's an integer because it's an integer. I care because I want to know that it's telling me that certain information's a count. Or I don't necessarily care if something's like a binary field in terms of its encoding, but I care that it's like always going to be 0 and 1 because that means I can take the average of it and calculate a proportion. Maybe I don't want to do that. So I think it's a mix that it does get close to encoding just like type information, but typically I try to like nudge stubs towards, I guess, combining both like that technical information with a sense of semantic information as well.
Okay, our next question is from Bing Wu, who asks, how do column name as a contract handle semantic changes? For example, a nullable column becomes not null only in the future. Does that mean the column should be renamed?
As like kind of this framework exists today, I think my gut reaction would be yes. You can certainly imagine that there are many downsides to that approach in terms of let me say it this way. I think the downsides and the upsides to that approach are exactly the same. On one hand, it could be annoying for users to have to go back, change that column name. But at the same time, if we are changing something so fundamental in the data as allowing it to have nulls where it didn't have it before, users will probably, unless they are made aware and forced to confront that, carry their previous understanding of what was allowed in that data with them. So I think by changing the column name, I think there's almost a benefit of failing noisily and just forcing people to confront that change and accept it and internalize what that actually should mean for them and for their work.
That's a great answer. I see a lot of analogy there, but just between DBT tests as a whole, when there's the miscommunication in your data source to the data you're building, and how that test can really tell you when those underlying changes happen that you're unaware of.
Yeah.
That answer really resonates with me. We have another question from Anders in the chat, who says, I love the perspective brought to SQL via dplyr. As a dplyr stan myself, that was forced to learn pandas when I switched jobs, SQL and DBT was a breath of fresh air to me. What dplyr conventions and experiences do you love that are still missing from Jinja and SQL?
That is definitely a great question, because I definitely have spent quite a lot of time in the R community myself, and am a huge fan, I think, of just their workflow and style. I think that is definitely something that I will say attracted me to the DBT community, because I think a lot of the things that I see a lot of similarities in the workflow of making things more modular and reproducible. I think DBT has now probably extended a lot of the functionality that I would have felt was missing from pure SQL, like getting into a little more of the tidyr space, making it easier to pivot data, which isn't available in all SQL syntaxes, and do a lot of those things. I think probably the biggest thing that I, as an R user, love that is not really something that is easy to do in SQL, but I think it's probably more of a database thing than strictly a DBT thing, is in R, I'm a huge fan of list columns and nesting data and having a data set of data sets. Of course, in SQL, you can do similar things with putting a lot of JSON in a column or something, but I think that's one really native to our workflow that I really love and I really miss when I'm using a different language.
I totally see that. Okay, I'm going to go ahead and choose this next question based on a personal bias of, I also had this question roughly typed out. Joel Labs asks, a lot of the magic of DBT is it's just SQL. As you wrap more macros into more of your code, that becomes less true, which can make it harder to onboard people. How do you think about those trade-offs? Is it worth it because your team are more effective and can ship more reliably? And then do you wind up internalizing the syntax eventually?
No, that is definitely I feel like the perpetual question between simplicity versus expediency in some ways that I definitely, no matter what language I'm doing, there's also always kind of a part of me that loves to resist using packages, see how far I can get on just the raw language itself. And I think there definitely is a cost that when things are just slightly prettier semantics, I tend to resist. I think the kind of macros I think that really excite me and really make me willing to start adding dependencies into my code are when I start getting to places where there are things that I think truly cannot be done just with the raw language itself. For example, I think something I really like, and I like with dbtplyr that I find very handy, is just to be able to say, yeah, take the sum of all these variables, or take the mean of all these variables, and not having to like manually type things out line by line. Because I think at some point I reached the other trade-off of like, there's risk from tools and dependencies, but there's also risk from human error. And I guess that's maybe the fundamental trade-off that I weigh of it's, if there's something I can like force to do relatively simply with no dependencies, that's probably the safer approach. But if there's something where like I'm at more risk myself of messing up, making a typo, doing something wrong, forgetting about a variable, or I just don't want to type 100 different column names that I want the sum of, that's maybe where the risk of the machine becomes less so than the risk of the human.